Good afternoon, everyone, and thanks for joining. I'll just give a couple of minutes for everyone to join. Give it one more minute, and I think we'll get started. Okay, let's get started. Good afternoon, everyone, and thanks for joining. My name is Lyndon Berwick, and today we are going to talk about contaminant removal from mining-influenced wastewater using permanganate oxidation. A couple of quick housekeeping items before we get started. Everyone will be in listen-only mode, so if you have questions throughout the webinar, please submit them through the questions pane, and we can follow up after the presentation if we have time, or if not, we can get in contact at a later date. So just a little about myself. I am a technical and field specialist with the Carus Technical Solutions Group. I've been with Carus for a little over 5 years now, since moving to the US from Australia in 2018. And I have over 20 years of chemistry experience in both research and industrial sectors. I completed a PhD in 2009 and then worked as a full-time research fellow with the Organic Geochemistry Centre at Curtin University in Western Australia. I then worked as a production chemist with Baker Hughes and was responsible for the on-site management and monitoring of the chemical treatment programs there for Chevron's oil and gas operations on Barrow Island in Western Australia. Over the last few years with Carus, I've been heavily involved in the mining sector, looking at solutions for the treatment of mining-influenced wastewater, amongst other mining-related applications such as mineral flotation chemistry. So now, while I'm the one presenting today, I just want to point out that all of the information generated here is a result of the hard work of numerous Carus colleagues, both past and present. So let's get going. These are today's main talking points. First, a little brief background about mining-influenced wastewater. Secondly, the types and the properties and reactions of permanganate that can assist in treating these types of waters. We'll then look at both field and laboratory data from several industry case studies and the key testing and results designed to address specific wastewater treatment goals. Some of this includes the types and concentrations of contaminants in different water types, optimization of oxidant and other chemical doses, the impact of pH, the impact of the order of chemical addition, and the use of coagulant and flocculant products. Finally, we'll highlight some of the key operational benefits observed to some of these particular applications. So there are numerous factors to consider for the treatment of the wastewater or processed water produced during mining operations or remediation type activities. Some of these include water scarcity and the potential requirements for water reuse or recycling, the type and concentration of contaminants like heavy metals or cyanide, the type of chemical, physical, and engineering treatment strategies that are used, and the specifics of the effluent discharge such as the discharge location, whether that may be city water or local water bodies, any specific permit requirements, and also toxicity testing. So we're obviously focused here on the use of chemical oxidants, which are often applied to precipitate soluble metals before the addition of coagulant and flocculant products for solid separation and water clarification downstream prior to discharge of that treated water. So what is permanganate? In chemistry terms, permanganate is a highly oxidized form of manganese. This is a transition metal that's very similar to iron. The products at Carus are available in different physical forms and compositions. We have crystalline powders, which are more concentrated but have a lower water solubility. But they're also available as diluted aqueous solutions, which can often be more convenient to receive and feed. Permanganate solutions will be light pink to dark purple in color, depending on the concentration of the solution. You can see that in the picture here, with increasing purple pinkish color with increasing concentration. Some of the major applications for permanganate include pretreatment of drinking water, treatment of municipal and industrial wastewater, soil remediation, odor control for things like H2S and mercaptans, oil field produced water treatment, and the oxidation of organic compounds. So there are obviously many different commercial oxidizers available, so why use permanganate? One of the major benefits is that permanganate reactions are extremely fast, so it can be used where that reaction or retention time in the process is limited. Some of the classic reactions with inorganic contaminants include oxidation of soluble iron to the insoluble iron oxides, oxidation of soluble manganese to insoluble manganese oxides, the rapid oxidation of reduced sulfur compounds like hydrogen sulfide, and also the oxidation of pyrophoric iron sulfide, which is commonly used during refinery turnarounds and tank cleanings in the oil and gas industry. So with that brief background info covered, let's dive straight in and look at a case study that we've done extensive work on here at Carus. This study focused on thallium removal from wastewater at a gold mining operation in South Carolina. Thallium is a highly toxic heavy metal that is soluble over a really wide pH range. The leaching of thallium during processing of various mineral ores can often exceed the discharge limits or regulations in mining water effluents. The Haley Gold Mine is located in Kershaw, South Carolina. In 2021, the operating company Oceana Gold approached Carus to replace their existing hypochlorite or bleach oxidation with our Carusol C liquid permanganate product in an attempt to try to help optimize their wastewater treatment process. Some of the issues with hypochlorite, the previous treatment included potential generation of chlorine gas at low pH, which nobody wants, inefficient removal of iron and manganese, which was contributing to significant fouling of the microfiltration process at the downstream end of the treatment system. And we also looked at residual chlorine in the effluent discharge, which often required the use of sodium bisulfite as a reducer to dechlorinate the water prior to discharge to their outfall. So the key operational goals that we targeted with permanganate treatment included safe, efficient, and consistent thallium removal, which is one of the key parameters monitored for the, let me go back here, for the mine's discharge permit, efficient removal of other metals of concern like iron and manganese, improved performance and cleaning of the downstream microfiltration system, and also in situ process control and monitoring for parameters like permanganate residual, metal concentrations, and oxidation reduction potential. So with these operational goals in mind, our lab studies were focused on 4 main areas. the impact of varying permanganate doses on thallium, iron, and manganese removal, the impact of the order of chemical addition on metals removal performance, the impact on performance with and without ferric chloride coagulant, and as I said, also analytical methods for in situ monitoring of permanganate residuals. The lab jar testing procedure that we use was designed to closely mimic the wastewater treatment process at the mine. So the basic schematic is shown here, nothing complicated. Water from the waste pond is dosed with permanganate on its way to the reaction tank or oxidation tank. Hydrated lime is added for pH adjustment, followed by ferric chloride coagulant, and then flocculant is added to flock and drop the solids in a multi-flow clarifier. In the jar test experiments, we both filtered and unfiltered aliquots of the supernatant were collected for further analysis of total and dissolved metals after the solids had settled. So let's look at some of the key data from this particular study. The first data set here shows the carousel seed dose response for total thallium removal. The plant operates at a pH of around 9. So if we focus just on the blue data points here, we can see a clear linear response for thallium removal and an optimized dose of around 35 ppm. This dose was able to reduce thallium to the target level of less than 0.2 micrograms per liter, or ppb, so really low levels. We also wanted to look at the impact of pH and whether we could achieve more efficient thallium removal using a lower carousel seed dose at higher pH. The brown data points here show that there isn't really any significant difference in thallium removal by increasing that pH to 9.5. The next data set here and our next focus shows an evaluation of the impact of the order of chemical addition on thallium removal. The data in blue shows thallium removal using the current strategy of applying oxidant first, then adjusting the pH with lime, which is commonly done. The data in brown, on the other hand, shows thallium removal by adjusting the pH before adding the oxidant. So we can see there was about a 20% reduction in the carousel dose required to achieve the target thallium level by adjusting the pH first. Again, the aim here was to try to optimize the process and provide the plant with options for potentially reducing their chemical usage and the overall cost of treatment. So with thallium removal being one of the key process treatment goals, the slide here shows a brief overview of the removal mechanisms taking place. Permanganate oxidizers dissolve thallium as well as other major metal components like iron and manganese, as I mentioned. The key reactions are listed down here in equations 1 to 3. I won't go into too much detail, but essentially the insoluble precipitates that form from these metals can then be removed by coagulation and flocculation. So manganese oxide precipitates are also generated during the reaction, and I'll touch on this a little bit further down as a byproduct of the permanganate oxidation. So these manganese oxides that are produced so facilitate thallium, iron, and manganese removal through a combination of precipitation, co-precipitation, and adsorption at alkaline pH levels. So with these mechanisms in mind, we know that the permanganate will also react with other metal components in the wastewater, which are typically present at much higher levels than thallium. The permanganate or oxidant demand is mainly consumed by these more highly concentrated compounds like dissolved iron and manganese. These metals can also cause significant fouling of the microfiltration units and reduce the overall throughput volume in the plant. The data here shows a clear dose response for iron and manganese removal. At the optimal 35 ppm dose that we saw for thallium, we can see that iron is below detection limits and manganese reduced below 1 ppm. Permanganate, as I mentioned before, is much faster than hypochlorite, particularly for manganese oxidation, and so it doesn't require those. Also doesn't require those excessive feed rates. The flow and effects of this mean that fouling, increased plant throughput, and a reduction in chemical costs associated with neutralizing residual chlorine in the effluent that was required when they were using bleach as the oxidizer. So the next slide here highlights the permanganate half of the oxidation reaction. The colors I've got here, the purple and brown, are deliberate. When permanganate is dissolved in water, the solution has that distinctive pink to purple color, as I showed previously. The precipitated byproduct of the oxidation reaction is a brown solid called manganese dioxide, MnO2. MnO2 is actually a very useful flocculant material that can play an important role in water and wastewater treatment after the oxidation step. So it can act as a coagulant aid or seed material that is interactive with inorganic coagulants and polymers. It can help adsorb other impurities such as positively charged ions and some organics. And it also provides an active surface for the oxidation of sulfides by dissolved oxygen. So we wanted to look more closely at the potential advantages of this manganese reaction product for the Oceania gold system. The data here on the left shows the impact of adding ferric chloride coagulant on total thallium removal. We can see there's really no significant difference in performance with or without coagulant, effectively meaning that this chemical can be eliminated from the treatment strategy because that MnO2 that we generate is acting as its own coagulant. We also wanted to look at thallium removal in response to different influent water characteristics. So the main concern in this case is that with low incoming dissolved ion concentrations, there may not be enough precipitated material or solid material after the oxidation step to achieve sufficient solid settling during clarification step. So the plot on the right here shows that this actually isn't the case. Effective thallium removal was achieved with both high and low incoming ion levels. You can see here 31 parts incoming ion compared to 3 parts incoming ion, 10 times difference. Same removal efficiency, again, without the need to add coagulant. We've seen similar benefits in oil field produced water treatment applications using permanganate, where ion removal is a really key priority for those applications. So another really important consideration for process control is to make sure that we don't overfeed the permanganate and carry a residual to the discharge point. This can potentially affect downstream conditions such as whole effluent toxicity testing. This was an issue with the previous treatment where hypochlorite or bleach could actually carry free chlorine to the effluent and influence those wet test results. So we looked at several methods to track permanganate residual in the process. These included oxidation reduction potential, ORP, UV vis testing for a direct read of that characteristic pink color, ARC DPD free chlorine testing, which can also be used to measure permanganate, and our own Carus carrier test amperometric cell testing. What we found was that the changing makeup of the influent process water, depending on rainfall, seasonal events, meant that the baseline readings for both ORP and the carrier test were not at 0 millivolts. So when no permanganate, so these were eliminated as potential online monitoring options. On the other hand, both the UV vis and the DPD testing showed a stable baseline and immediate response when permanganate was present in excess levels. DPD online analyzers are readily available, easy to use, and so this method would make for a good process control to ensure no overfeed of permanganate during the treatment process. The plant at Oceania, at the gold mine, Haley Gold Mine, continues to carry out spot tests several times a day using this, really easy approach. So to summarize the major findings from our laboratory studies, thallium removal increases with carousel seed dose, as you would expect, along with iron and manganese removal. Thallium removal efficiency can be increased by using pH adjustment before adding the oxidant. Ferric chloride coagulant addition can be eliminated from the treatment process because that manganese dioxide byproduct provides an excellent in situ coagulation aid. And finally, UV-Vis or HYPE DPD methods to evaluate a potential permanganate overfeed are consistent and accurate and largely eliminate the need to remove excess oxidant with sodium bisulfite that was previously required using treatment with bleach or hypochlorite. From a operational perspective, some of the key operational benefits that the plant has observed since treatment included increased thallium removal to less than 0.2 ppb or micrograms per litre. This is despite influent thallium concentrations increasing. This has allowed greater operational flexibility while still maintaining comfortably below their permitted levels. Cleaning frequency for the microfiltration unit was reduced by 75% due to that improved removal of foulants like iron and manganese. And a final flow on from this was that the water treatment plant was able to significantly increase their overall throughput and discharge volume. For example, since implementing permanganate treatment, since it started in April 2021, the total discharge volume almost doubled in April and May compared to March and previous months. So let's move on now to a second case study. This is based on work performed at a metal smelting plant in the Midwest. The removal of thallium was again a key priority here for permanganate treatment, but there were also concerns with other heavy metals like lead and cadmium. I'm sure most people are aware of the issues with lead toxicity. Lead exposure through mining, smelting, and battery manufacturing, disposal, and recycling is a global concern. So cadmium may be a little less well known, but it's also a toxic and environmental hazard. Human exposure to cadmium can occur through fossil fuel combustion, phosphate fertilizers, iron and steel production, cement production, and municipal solid waste incineration. So jar test studies here were performed to look at thallium, lead, and cadmium removal compared with the incumbent treatment strategy, which was sodium sulfide. Now, clearly, oxidation is certainly required for effective thallium removal, as we saw with the Oceana Gold case study, but lead and cadmium removal is mainly based on precipitation by pH adjustment to those alkaline conditions. So the key here was to ensure that thallium treatment with permanganate didn't adversely affect the lead or cadmium removal. This experimental procedure is again similar to what we described before: oxidation and pH adjustment, followed by coagulant polymer addition for those solid settling. So the concentrations of each metal at the time of sampling were around 95 micrograms per litre or ppb total lead, 19 ppb total cadmium, and 20 ppb total thallium. The treatment goal is to maintain monthly effluent discharge below 6.3 ppb thallium, 1.1 cadmium, and 7.9 lead. The graph here shows the percentage removal of each metal at different doses of permanganate. The solid lines are for the permanganate treatment, while the dashed lines show the percent removal using sodium sulfide, which was around 50 ppm. So we could clearly see that permanganate achieves well over 90% removal for all three of those metals, and in particular clearly achieves much higher removal of the thallium component, which is shown in the blue lines. So in terms of plant application, Optimizing the permanganate dose showed removal of each metal contaminant well below the required discharge limits, and it was also achieved at about 100 times lower dose than what was required for sodium sulfide. So, excellent result, and of course, any of those health and safety concerns around the use of sulfides were reduced or eliminated. So let's move on now and look more closely at iron and manganese removal. These metals don't necessarily pose a specific toxicity risk, but they do have issues in potable water treatment, such as scaling of pipework, fouling of filtration equipment, as I mentioned before, aesthetic problems like taste, odor, and color in drinking water that's delivered to customer homes. In terms of mining treatment, one of the major issues for iron and manganese occurs for acid mine drainage. Surface and deep shaft coal mining operations have to meet EPA standards for the amount of acid, iron, and manganese in their drainage waters. As I've mentioned before, iron and manganese removal is really the bread and butter for permanganate treatment. Some of the key treatment targets and advantages include rapid oxidation of dissolved iron and manganese. There's need for pH adjustment if it's not required, although adjustment prior to permanganate addition or oxidant addition can potentially be more cost effective. We can also see enhanced solid liquid settling in holding ponds prior to discharge. The effectiveness of the coagulation process results in better filter run-in times. Permanganate also doesn't form potentially toxic chlorinated organics, which can find their way into drinking water, and the products are relatively safe and easy to handle. So let's look at a third case study now, this time from a coal mine in Ohio. This was a 203-acre surface coal mine that was exceeding the NPDES, which is National Pollutant Discharge Elimination System, exceeding that for total manganese at 2 ppm, milligrams per litre. The problem area, specifically at pit number 4, contained runoff and leachate materials with manganese in the range 4 to 15 ppm and iron in the range 1 to 76 ppm. So the chemical application strategy here was very simple, simply due to the fact that it was a remote location with no available power. Carus, our liquid permanganate product, was simply gravity fed into the runoff stream. Chemical dose was adjusted manually based on the color change with the oxidation rate and the runoff stream flow rate, that purple to brown oxidation color change. The plots here show the outfall monitoring data over a 6-month period. The total flow and run times were maintained within the operational requirements, and the total manganese concentration was consistently held below the discharge limit of 2 ppm, with a 6-month average of just 0.81 ppm. This is a second acid mine drainage case study from, again, a coal mining operation in West Virginia. The challenge for this site was to, again, reduce high iron and manganese levels in the wastewater. So drainage water samples were collected. The analysis showed a pH of 3.9, iron at 45 milligrams per litre, and manganese at 10 milligrams per litre. The facility was required to reduce manganese down to less than 1. So the treatment strategy, after the pH was adjusted to 7 or above, most of the iron was precipitated, and the Carus liquid permanganate was able to significantly lower the manganese concentration. Carus dose of just 10 milligrams per litre was able to reduce the iron to 0.35, 0.4 ppm, and the manganese to 0.75 milligrams per litre. We've seen very similar results for removal of these common metals at another coal mining facility in Kentucky, again using pH first, followed by permanganate oxidation. Key point here, the pH adjustment, and it's part of the overall treatment strategy and goal. pH adjustment to above 7 is important for a few reasons. One, it raises the drainage pH to within EPA guidelines, which is typically between 6 and 9 pH units. The iron precipitates in the wastewater as iron hydroxides, and it then reduces the overall permanganate demand and treatment costs by removing most of the iron demand and some of the manganese. Our next application looks at arsenic removal, which is becoming more prevalent in mining influenced wastewater. Arsenic is particularly potent, as I'm sure everyone's aware. It occurs in many minerals and usually in combination with sulfur and metals. So sources of human exposure include weathering of minerals and ores, mineralized groundwater, and inhalation of atmospheric gases and dust. The advantages of using permanganate for arsenic removal include rapid oxidation of arsenic to very low levels, while also oxidizing iron and manganese, a common theme here. The manganese dioxide can adsorb arsenic 5, as we discussed previously for some of the other key metals of concern. Iron oxidized by permanganate can also adsorb arsenic, meaning the addition of iron coagulants is often not necessary. And there's also no formation of in organic laden waters. So our next case study here, case study number 5, looks at arsenic removal from a pit dewatering operation in North America. An effluent treatment plant was built to accelerate the dewatering of the pit, which contained 80 to 90 million meters cubed of water accumulated since 1930 during previous mining operations. The pit bed here is unlined and contains arsenopyrite, with dewatering to take place over several years. Water quality analysis of the influent water showed a neutral pH with negative ORP and revealed 2 major elements of concern: arsenic and cobalt. The treatment process is required to meet parts per billion level discharge limits prior to discharge to a nearby river. The basic treatment process is similar to many other MIW treatment programs. Firstly, oxidation with Carus liquid permanganate, with the permanganate visually, solids coagulation with ferric sulfate, pH adjustment with lime up to 10.6 units. This is mainly to prevent the cobalt escaping the plant. Then obviously flocculation and clarification with a cationic polymer, filtration with 200 micron pre-filters, and if necessary, if there is some solids carryover or fine solids carryover, a 5 micron ultrafiltration step if required. And then the sludge is transferred to geotubes for dewatering to 50% solids, with the dewatered sludge landfilled to a tailings area. So the challenge for this site was to lower arsenic to less than 9 parts per billion and cobalt to less than 7 parts per billion. So really, really low levels. The solution, again, to use Carus liquid permanganate. The treatment strategy ongoing, 2,000 meters cubed per hour of pit water was treated using 20 liters per hour of Carus and 30 liters per hour of ferric sulfate, 24 hours per day. The results showed that both arsenic and cobalt were reduced below required limits using just 10 ppm of Carus and gave a positive ORP after treatment. And one final case study here. This is again for arsenic removal, this time using a green sand filtration process. The challenge for this site was to lower arsenic from 125 parts per billion to a goal of less than 5. The solution this time was to operate the green sand filter in continuous regeneration mode with Carus potassium permanganate addition, so our solid product. The results showed 96% removal of arsenic from 125 parts per billion to down to less than 5 parts per billion. Iron and manganese, again, common theme, were also reduced to very low ppb levels and no additional iron coagulant was required in this process. So just to briefly summarize, hopefully the key takeaways from this presentation: permanganate is a strong, stable oxidizing agent used extensively in water and wastewater treatment. It's safe and easy to handle, and offers a rapid and effective treatment alternative to other commercial oxidizers. It targets a variety of metal contaminants, including iron, manganese, thallium, and arsenic. Also cyanide, which hasn't been covered in this particular presentation, but also very effective for cyanide. It can provide an excellent in situ coagulation aid for solids removal and water clarification, and can potentially eliminate the need to add inorganic coagulant or reduce the required doses of polymer flocculant products. It can provide more consistent treatment efficiency and performance for variable wastewater types, and can also help overcome effluent toxicity issues encountered with other oxidizers, particularly bleach. So hopefully this presentation has demonstrated our technical expertise to help evaluate and optimize performance in the treatment of mining influenced wastewaters. Carus has been a world leader in the production of permanganate oxidants for more than 100 years, the only US manufacturer of permanganate. In addition to our permanganate and other oxidation product blends, we can also provide a variety of coagulants, polymers, and catalyst technologies. We have a dedicated mining lab for analytical testing, consultation questions, and treatability and feasibility studies. And also, as a key part of our technical support, we provide extensive field application services, including on-site testing, treatment assistance, chemical feed system design, and installation, and also online analytical equipment. So just to wrap up, here are our contact details. Please feel free to reach out to us for further information or one-on-one consultations to see how we can help you with your specific wastewater treatment goals. I appreciate and thank everyone for your time today, and I'm of course happy to answer any questions that you may have. Thank you. Get to the questions pane and see if there's anything there. Doesn't appear to be any questions coming through, but as I said, please reach out to us for further information or one-on-one consultations, and we're happy to help. We're here to help. Again, thanks everyone for their time and attention today, and have a good afternoon.